Good evening. My name is Shannon Higgins, and today I'll be presenting to you my research study entitled The Diatomic Molecular Database of Dissociation and Spectroscopic Energies, also known as DMDSE. The following slide will be the outline I will be following for this presentation. The internet has proven to be both a blessing and a curse to the furthering of humanity's knowledge. On one hand, finding information on a topic of interest has never been easier, and this is especially true in the case of scientific subjects with such a grand amount of articles, videos, and other resources available for one to teach themselves about whatever topic they desire. On the other hand, however, the sheer abundance of information available online is not always there to aid someone's personal education. For example, according to a 2009 study published by Sage Journals entitled Investigation of the Accuracy of Search Engine Hit Counts, an investigation was conducted on the accuracy of hit counts for popular search engines such as Google and Microsoft Live Search. It was determined that the accuracy of search algorithms differed immensely between engines, specifically the number of words typed into the search bars of respective engines drastically affecting accurate queries. Imagine you're trying to conduct a study on the differences of water quality between beaches located in your state, and you go to Google to collect more information on the subject. The way you type your question in the search engine, however, ends up confusing the engine. Maybe you worded it unusually or forgot a crucial word, but nevertheless, your results are filled with outdated and incorrect information, which is no way to begin an investigation. With the internet's fundamental purpose to share information with billions around the world and learn from others ourselves, this is an example of a glaring issue that interferes with the potential education of users, especially users interested in furthering their scientific knowledge. The fact of the matter is that the internet is intertwined with science, and the relative lack of data accessibility can serve as a barrier for conducting research that can innovate any field of choice. An example of this would be the field of atomic and molecular physics/chemistry, which involves research consisting of data relatively difficult to find. Statistical information on diatomic molecules, spectroscopic constants, and others are often spread out among several databases, scholarly articles, and websites alike, making acquiring this information in the first place time-consuming and immensely tedious. This brings up the question: how can categories of information existing in these niche fields of physics and chemistry be compiled into one source, easily accessible for both research and educational purposes? This question leads into its potential answer. It can be hypothesized that if dissociation and spectroscopic energies are collected, it can be used to create a user-friendly diatomic molecular database with the purpose of compiling and sharing statistical information. This database is labeled the Diatomic Molecular Database of Dissociation and Spectroscopic Energies, which will be referred to as DMDSE moving forward. To begin discussion on DMDNC and its functionality, an examination must be done on its design philosophy. At a fundamental level, DMDSE is designed with the purpose of providing an interface dedicated to user-friendliness and efficiency, and is also designed to be an expansion of existing sources committed to assembling similar information categories. Two of these sources are the Database of Spectroscopic Constants of Diatomic Molecules, and the Diatomic Molecular Spectroscopy Database, operated by Stony Brook University and the Fritz Haber Institute of the Max Planck Society, respectively. An important distinction to make is that DMDSE is an independent property, and only serves as an expansion in the sense that it contains information already available in these sources, but also contains more data than what is accessible. Both of these databases serve as models and examples behind DMDSE and its future applications. The majority of DMDSE development was done using MySQL, an open-source relational database management system, with programming done in Visual Studio Code and SQL Server Management Studio. Data was collected in Google Sheets, and DMDSE itself was constructed using structured query language. For example, the tables of data categorization were connected through the establishment of relationships using identification commands, which served to connect molecules to their respective data categories. These specific commands served as primary keys, which allowed for the tables to be independent from one another but still connected. To represent this visually, DMDSE functioned like this chart here. A user would first input a molecular/chemical formula into a provided search engine. This would prompt a connection to the database situated in MySQL, and data corresponding to the user's input would be presented in a quick, efficient manner. If the user has contributions to existing data, they would enact a function to contribute data previously unregistered, and once done, a prompt would be enacted to send a message of confirmation to the email provided by the user. Although DMDSC is still in its infancy, many future aspirations will be considered as development continues. Such aspirations include to publish it to a wider audience in the form of a public website, as well as implementation functions such as machine learning and graphical plotting tools. Here are my references. Please consult me if you have any questions, and thank you for your time.